Hello and welcome to another live stream of Chemistry 223. This is week 7. I hope you're all having a great term so far. Got a few more weeks left in this term, and let's talk about what we're going to talk about today. Today we're going to talk about oxidation numbers and um, galvanic cells, as well as kind of the different cell notations of galvanic cells and how to write them down and do that. First, let's talk about a little bit of the links and services we provide here at the Learning Center. So here's a link in the chat for the Learning Center. That's www.pdx.edu/learning-center/tutoring. You can definitely find out any of the services we have there, which includes academic counseling and tutoring for various different subjects. You can also check out the Pingy app and sign into that to see a schedule of all of our great tutors that we have here and schedule an appointment with them. You can also follow the Learning Center on Facebook and Instagram. The links are going in the chat for there. Just stay in touch and get notifications anytime we provide new services such as this live stream and other things like that. Also, definitely check out our recorded videos on the Learning Center's YouTube page. And you should be able to get to that through the Instagram or Facebook links. Also, just search YouTube for Portland State University Learning Center, and you should see a playlist for the Chemistry 223, and you see all the past videos that we have there for that. So let's get started today, starting out talking about oxidation numbers. So oxidation numbers are essentially talking about the relative charge that a certain atom has within the species that it's in. And when we talk about elemental atoms, they have an oxidation number of 0. These elemental atoms are stuff like, you can think of it as copper, Cu, solid, gold, solid, etc. Anything that's kind of in its pure state, it's not ionized in any way, shape, or form, there's going to have an oxidation number of 0. So that's silver. Actually, gold is Au, and so on and so forth. So any of the elemental charges, they have an oxidation number of 0. But when we have these atoms mixed into a molecule or they're ionized floating around in an aqueous solution, then they have an oxidation number which is equal to their charge. So I can say atoms in a molecule or solution have an oxidation number equal to their charge. So some relative examples of that would be like copper 2 plus in aqueous solution, silver plus in an aqueous solution, so on and so forth. There's lots of different ionized metals that float around in there, and anytime they have a charge associated with them, for example, this copper 2 plus would have an oxidation number of 2, and silver would have an oxidation number of 1. And there's a lot of these different ions we see floating around in there, and anytime we go from like a solid with an oxidation number of 0 to a copper ion, for example, solid copper to copper ion, we say that's a redox reaction. So it's an oxidating reaction because it's losing electrons. It goes from a neutral charge to a positive charge, which means it has to lose electrons in that process. So we call that oxidation. I'll say that's the loss of electrons. And it usually means that from the initial state to the final state, the atom has gotten more positively charged. So, for example, that if you have a copper solid turning into copper 2 plus, it would also have 2 electrons. Let's write that proper, 2 in front, E minus. And you notice that we have a balance of charge on both sides of that equation now. Where on the left side we had neutrally charged, on the right side we have that copper 2 plus, we have to add to that 2 negatively charged electrons, so the net charge on the right side of it matches the net charge on the left side. We could also see this as like an iron 2 plus, which can be aqueous, and that would turn into, let's say, iron 3 plus plus an electron. And this is also aqueous. So you notice in this case, our iron was charged and had an oxidation number of 2, but it moved over and got an oxidation number of 3, and in doing that, it shed an electron from it as well. So these are different examples of oxidation. When we talk about reduction, it's kind of the opposite effect happening. So for reduction is when you would have, we would gain electrons. Or we think of it as it's becoming more negatively charged, or going from a positive to a neutral is another version of becoming more negatively charged. Anytime we're gaining electrons in that process, it's going to happen to be a reduction reaction. And some examples of that is kind of just the opposite of what we had there. If I had copper 2 plus, then I would have to add 2 electrons to it, and it would produce a copper solid. Or if I had like silver plus, I could add 1 electron to that, and we would end up with a solid silver. Just some examples of reduction reactions. They're going from a positive charge to a neutral charge in these situations. Notice that in a reduction reaction, the electrons are a part of the reactants, while in an oxidation reaction, the electrons are more part of the products. And you're going to see that's a common thing, usually because of how those electrons have to move. By losing the electrons get split from the reactants and forming the new products. They're kind of floating around. They've lost those electrons. In the reduction reactions, they start off positively charged, and we're adding that electron as a reactant to create this neutrally charged reduction product. And since most redox reactions, pretty much all of them, are going to incur in water that we're going to deal with, we can assume any time that we're dealing with these, that oxygen, so O, has a charge of -2. I'm going to say 2 minus. And hydrogens have a charge of +1. And this is useful when we talk about balancing our redox reactions, which is what I'm going to go into next. Let's right over here. So for balancing redox reactions, there's a certain set of steps that we can basically follow to make sure we get this in the correct order. Usually it has to come with starting out with just these basic half reactions, looking at how the reaction starts and what that redox reaction or the oxidation or reduction is going on. And then we add into it water for all the oxygens that we might need in that reaction, and then balance it with hydrogens. So let's write those out. And then we can add our electrons at the end. So the first thing we do is write a skeletal equation for the oxidation slash reduction. TI, I had it right. And these we call half reactions. And this kind of looks like what I did on this previous page here. These are kind of examples of those half reactions. We're not looking at the full reaction of things. We're just looking at how does copper change. It goes from a solid, in this case, to a +2, and it produces 2 electrons. That's kind of the half reaction of that oxidation. Similarly, when the copper or the silver, in this case, is we add electrons to it, it's getting those electrons. It's a reduction reaction. So those are the type of half reactions that we would add at that first stage of that balancing. It's just doing that. At the second stage, we want to balance each half reaction for oxygen by adding H2O. And we do that, we were just balancing those reactions by adding oxygen in anytime we need to. And we do that for kind of the charge balance between everything. A lot of times those electrons have to come from somewhere, and since they're floating in an aqueous solution, the O is going to be a part of that reaction. Then we balance it. First, I guess we balance it for everything besides hydrogen and oxygen. Let me move that down. Sorry, I skipped a step. Balance reaction for all elements besides oxygen and hydrogen. The third step is balancing it with the oxygen in there. And then the fourth step is then balancing the hydrogens, the H plus in the half reaction. Once we do that, we can add basically the electrons just to balance the charge on either side of those. So now we're going to add electrons to balance the charge. And this has to be done to make sure you have the same charge on the reactant and product side of the reaction, because you can never have a difference in charge. We can never lose those things. Worst case, we're losing them in the form of electrons. We have to note that on the product side, or we're gaining them from gaining electrons. We have to note that on the product side. So the sixth step is to just multiply one or both of those half reactions so the number of electrons consumed is equal to the number produced, because we need the same number of electrons to be consumed as produced in this whole situation. So we multiply, say, reactions. So number of electrons consumed is equal to the number produced. And we're looking at the comparison between the two half reactions. Really, we want the number produced in one half reaction to equal the number consumed by the other half reaction. And then we add these reactions together. Just kind of adding the products on one side, adding the reactants on the other side, and canceling out any common values we have between the products and those reactants. At any time, if it's taking place in a basic medium, we can add OH minus ions to them. If it's taking place in just to neutralize any of the H plus ions that might be added. So in this step here, we added a bunch of H plus ions in there. So that's fine if it's the solutions or reactions happening in an acidic condition. But if we know it's happening in a basic solution, we have to add OH minus to it. So the last step, and this is conditional, if solution is basic, add OH minus to balance H plus. So let's go through an example of this and this is when I pulled out of the textbook, writing a balanced equation representing the reaction between solid copper and nitric acid to yield aqueous copper 2 ions and nitrogen monoxide gas. So the first step was to write a skeletal equation for the reduction and oxidation half reactions. So start with the reduction. The reduction reaction, that's where it's gaining those electrons. So we're going from just to solid copper is Cu solid, nitric acid is going to be HNO3, and then aqueous copper 2 is going to be Cu2 plus aqueous, and the nitrogen monoxide gas is going to be NO gas. Just to make sure we know the compounds that are going into these, we can then start to see what the reaction is going to be for these things. So the reduction reaction is taking this HNO3, this nitric acid, and it's aqueous because it's an acid, it's floating in water, and it's going to produce this NO gas. That's kind of that basic skeletal structure of the reduction reaction. The oxidation reaction, that is going to be the copper. So copper goes from a solid to this aqueous 2 plus ion. So we can write that out there. Now step 2 was to balance each of those half reactions for all the elements except for hydrogen and oxygen. So looking at these, they're already mostly balanced. We can see that looking on this side, we have NO3, so really it's just the nitrogen we're looking at. There's one nitrogen, and there's one nitrogen. We're ignoring the hydrogens, we're ignoring the oxygens for this step. Same with the copper, there's one copper there, there's one copper there. So we're pretty much happy with this step. So I'm actually just going to copy all this down. I'll just put no change. This is no change to half reactions. Because everything except for the hydrogens and oxygens are already balanced. Step 3 was balance the half reaction by adding oxygen, or adding 4 oxygen, H2O. So in this case, we're looking at this top reaction here, and I'll rewrite it. We have HNO3 aqueous produces NO gas. Well, we know that that oxygen's not balanced. We need 2 more oxygens in there. So we can add to that 2 H2O. By adding that 2H2O, which is going to be a liquid, of course, now our oxygens are balanced. We're ignoring the idea of the hydrogens being unbalanced. We're going to deal with that in the next step. But at this point, our oxygens are balanced. Looking at the oxidation, Cu, solid, that's already basically completely balanced. We don't need to add anything to that for oxygens or hydrogens. The next step, step 4, is adding those hydrogens. So looking at the balanced equation that we have so far, or the not so balanced equation, we have 1 hydrogen on the right side here. We've got 4 hydrogens, 2 times the 2 hydrogens on that side there. So we need to balance this with this. So we can do that by adding H plus on the left-hand side of this equation. So I'm missing 3 hydrogens, right? So I can do 3 H plus, and it's going to be an aqueous H plus. Basically, some acid is going to have to be in there, plus HNO3 aqueous. It's going to produce NO gas plus 2H2O liquid. So now we've got our liquids balanced. Our oxygens balanced with 4 on each side. Our nitrogens started out balanced, so we're happy there. And now we have our hydrogens balanced as well. So now we need to balance the charge of each side of the reaction. If we notice the charge of, the total charge of this side of the reaction. I need to write my copper. Cu solid plus Cu2 plus as well. So we need to balance both of these reactions based on their charge for this next one. So for 5, we're balancing the charge. The charge for this top equation here on this side is 3, plus 3, because we have 3 positively charged hydrogens. This compound is neutral at this point. This compound is neutral, and water is neutral. So we need to add 3 electrons over here on this side to balance out to make it neutral like the right side here. So if I rewrite that, 3 electrons plus 3 hydrogen plus aqueous plus the HNO3. I'm just rewriting this side here. And the main thing I've added is I've balanced this side of the equation, because now that's a neutral charge. We would do the same thing with the copper. The copper solid produces this copper 2 plus, but we need to add, this is aqueous, we need to add to that 2 negatively charged electrons, because the copper 2 plus needs to be balanced with 2 electrons to make it neutral like the left-hand side of the equation. So now we want to try to make sure that we're balancing the number of electrons on the first equation with the second equation. The electrons produced needs to equal the electrons created or consumed. So in this case, the electrons consumed are these 3 up here, but we're only producing 2 electrons. So that we don't have enough electrons that we're producing to consume the other ones, and vice versa. So what we can do to that is multiply them by the the least common multiple of them, or to get the least common multiple, least common factor. So in this case, we're just multiplying this top one, this whole equation, multiply everything by 2. This bottom one, we multiply everything by 3. I can do that by, there's 3 electrons there, so I know I have to multiply this by 3. There's 2 electrons there, so I know I have to multiply those by 2. Doing that, I can see that this turns into 6 electrons plus 6 hydrogen plus aqueous plus 2 HNO3 aqueous, which produces 2NO gas plus 4H2O liquid. Doing that similar thing to the bottom, we end up with 3 copper solid, which produces 3 copper 2 plus 6 electrons. The last step is to add the 2 half reactions together. In this case, adding them together, first we want to look at kind of the product or the reactants there and the products here. Are there any common values we can cancel out? And the electrons are always going to be something you want to be able to cancel out of this, because the electrons just move around within this reaction. They're not usually a product of the reaction in the final end of everything. And then we just write all the reactants together and all the products together. So writing that out, there's going to be 6H plus aqueous plus 2HNO3 aqueous plus 3 copper solid. Those reactants will produce 2NO gas plus 3 copper 2 plus 4H2O liquid. And this should have been aqueous, and so should this. So now we basically have our final reaction. And the last step is to basically check, this is number 7. Does this happen in a basic solution? And if it does, we need to balance the H plus with the OH. In this case, it's happening we're adding nitric acid to it, so it's going to be more of an acidic solution. So we don't need to do that last step. And this ends up being kind of our final reaction for it all. I'll put a big box around it. There it is. That's the reaction that's actually happening. And see, it seems like a lot of steps. We kind of went through a bunch of them there. But really, I'm taking it one step at a time and breaking it down. We write our half reactions. These are the start and end reactions and what charges they are. Now, this is the reduction. This is the oxidation for them. Then we break it down and we try to make sure everything's balanced, ignoring oxygens and hydrogens. Then we add in the oxygens first. We add those in the form of water. And we do those first because with that water comes hydrogens. So if we did hydrogens first, we'd have to do hydrogens again and balance everything. So we balance those oxygens first by adding water to it. Because this is an aqueous solution, it's going to get its oxygens from water. Then we add in those hydrogens to them. Basically, how acidic does this solution have to be? And those extra hydrogens floating around in there will kind of balance the hydrogens on the other side of it. Then we add in those electrons. And the electrons are the key part because that's what's happening in this redox reaction. The electrons are flowing from some of the reactants to the products or vice versa, depending on which direction it's going, if it's oxidizing or if it's reducing ultimately. The last step is to add all those two equations together into one kind of net equation for this reaction. And that gives us this long ass thing. And usually we're able to cancel out the electrons when this is happening. So we get this nice long equation at the end of it showing how the reaction is happening and what the oxidation and reductions are going through. So let's move on to the galvanic cell. I got a nice diagram here of the galvanic cell. I'm going to kind of make a bunch of notes on top of that. But let's talk first about what the galvanic cell really is. And really it's just it's a use. It's a way that makes these redox reactions really useful in creating this electrical current flowing through them. And this electrical current is essentially the flow of electrons from one side to the other. And they happen because of this transfer of electrons in this redox reaction, the spontaneous flow of this. It only happens in spontaneous redox reactions. So I can say, oops, let's draw with the right. It's a redox reaction which causes a transfer of electrons through a circuit. But when I say circuit, I basically mean there's a path of the electrons flowing this way from one to another. It creates this flow of electrons. And in electronics, we call that a circuit. It's any path for electrons to travel, which produces, I'm going to skip over to the other side here. Maybe I'll just move this down. Producing an electrochemical cell. So that electrochemical cell is really what we're talking about. It's basically a battery that's happening. It's a really basic battery using two solutions where, in this case, we've got silver nitrate solution over here and copper nitrate solution over here. The copper nitrate solution has in it a copper anode, this copper solid metal sticking down into the solution. The solution on the right side has a silver cathode, okay, this silver bar solid sticking down into there. And we have a solution of silver nitrate and copper nitrate. And in between, down here, there's this salt bridge. This salt bridge is really sodium nitrate. That salt bridge is going to act to kind of balance the chemical charge within those baths, as these solutions, while this reaction is happening. And the anode here is connected through a wire to the cathode. So we're going to kind of break down what's all happening in this. So as this reaction starts to happen, just like we talked about previously, the silver, the solid silver, is going to go through a oxidation reaction, right? Because it's going to lose some of its electrons, and once it loses its electrons, it becomes copper 2+. That copper 2+ is going to become aqueous. It goes from a solid, because a solid copper is not soluble in water, but copper 2+ is because of that charge. So it's going to be floating around in that solution along with these nitrates that are here. And as they float around in there, more nitrates are going to come out of this solution. So I can start writing on here, this CO2 is, or Cu2+ is created by that oxidation reaction on this side of the equation. And this nitrate, NO3, is going to flow out of the salt bridge into the solution to balance that chemical charge. The charge on that left side wants to stay the same. So it's going to, that salt bridge releases the negatively charged anions, anions, to flow through there to keep us a balanced charge over here. But when this became copper 2+, we lost electrons. There's some electrons that were here, and they took off down this path through that circuit. And they followed this circuit around, ending up over here on the silver side. So now we have these electrons floating in there, and this silver is electrically charged. It's got these charges, and since opposites attract, the silver ions get attracted to those electrons. And when the electron combines with that silver ion, neutralizing the ion, becoming a reduction reaction. And this silver forms silver solid on the surface of the solid silver. So the solid silver actually grows a little bit. Over here, the copper is actually shrinking a little bit. Eventually, this copper will actually kind of wear down into a tip if you leave it in there for long enough, if you have a strong enough acid mixed in there. But usually, it kind of uses up all of that it can before all that happens. So when this silver bonds to that silver and deionizes, it needs to balance this charge as well in this solution. And it does that, if I can spell, I wouldn't be a scientist. If it does that by releasing sodium ions floating in there, and they're in an inert ionic structure, it's just there to balance that charge in that solution as well. So we end up with that balanced solution. The salt bridge is really used for counter ions. And they get fed back into the solutions. This porous plug is to make sure they don't just they don't just bleed into it. They have to actually have a pretty strong attractive charge to get through them. And then the flow of electrons, these electrons, like I said, flow along this into here, which causes those silver ions to bond to them. And that's the basic idea and theory behind that galvanic cell. And there's some notation for some of these, for these types of reactions when we write them out, because we can use different types of metals for this. We can use different anodes. The part that gets oxidized is called the anode. Part that gets reduced is usually the cathode. And in this case, we call this an active electrode. These are active. And what I mean by active electrode is the metal electrode that's going down in here itself, it's actually part of the reaction. Sometimes we use inert electrodes, such as palladium or platinum, to transfer those electrons into our solution and cause that reduction reaction within the solution. So it'll go from like a +4 to a +2, and that palladium is used to, or I'm sorry, the platinum is used to just transfer the electrons down. So the notation that we use for this, do I have space over here? Yeah, I think so. This is cell notation. And if I were to write out that reaction for this galvanic cell, notice we have copper 2 turning into copper, or we have copper solid turning into copper +2. We have silver plus turning into silver solid. So we can write out that whole equation. I'm just going to write it out up top. Plus, say silver plus aqueous. Those are basically producing copper +2, aqueous plus silver solid. To balance the charge of all of these, I'm going to need 2 on that side because I have a +2 over there, which gives me 2 on this side as well. Zoom in a little bit. So that's the basic chemical reaction that's happening, but that's not cell notation. To get it into cell notation, we write it in a specific way so we can see the different stages and phases of the cell as it transfers. So I would start by saying each half cell is represented by its chemical formula. An example of this here, for this type of cell, the chemical formula is really just this copper and this solid silver. So I'm going to write that copper on one side, and usually the anode goes on the left and the cathode goes on the right. So I'm going to write the cathode over here, like that. So that's how we start things off, just by writing each half cell represented just by its chemical formula. And then we talk about the interfaces, which are represented by kind of a vertical line. Okay, which basically just look like that. I'll put little quotes around it. Just a big long line. And we can write those out. And the interface tells it like what happens with the copper. The copper in this case goes into that solution with that copper nitrate. So I can write that Cu solid interfaces with Cu copper nitrate, NO3 2 aqueous. Going from the right side, I can say silver solid interfaces with silver nitrate. Oops. Big O. And we're still keeping them separated at the moment. We combine those together with kind of a double line in the middle. And then basically the last step is to write it kind of from left to right, anode to cathode, and then separating it by that double line. I like to think of that double line representing the salt bridge between them, because that salt bridge kind of feeds both of them back out. But what that salt is made out of doesn't matter nearly as much, because it's usually just going to be some spectator counter ion balancing the charge of both of those solutions. So last step, beginning with anode, write all identifying phases and interfaces. And then I can just say end with the cathode. And remember that the anode is going to be our oxidation. The cathode is going to be our reduction. And remember, the oxidation is losing the electrons. So it's going from neutral to positive, or it's going from positive to more positive. Where the reduction is gaining those electrons in. So it's going from positive to neutral, or it's going from neutral to negative, or even say positive to less positive. Those are the different types of reactions you might have. But always, if you're gaining electrons, it's going to be reduction. If you're losing electrons, it's going to be an oxidation. So let's try this out in an example. We got two examples we can run through. So here we have a galvanic cell, which is fabricated by connecting two half cells with a salt bridge, just like our normal diagram said. One of which is a chromium wire is immersed in 1 molar of CrCl, or CrCl3 solution. Another with a copper wire immersed with CuCl3. Assuming the chromium wire function as an anode, the chromium functions right. The schematic for the cell, along with the equations for the anode half reaction and the cathode half reaction. So looking back on what we just talked about, we always begin with the anode, work our way to the cathode. In this case, we know, just writing the chromium, which is Cr, we write on the left side. And then on the right side, we would write our copper. That's going to be a solid as well. So we can then write these half reactions for everything. So the anode, this would be, again, the oxidation reaction. It's going to lose its electrons. So we know that some chromium solid has to produce, and it says here chromium Cl3 is what we're looking at. So the charge for chromium, after this is all said and done, is going to have to be a +3 to balance the 3 negative charge chlorines on the other side. So, because each of those chlorines has a -1 charge to it, adding 3 to that gives that chromium in that molecule a 3+. Aqueous. We know that. And then, because of that 3+ to balance the electrons, we can add to that 3 negatively charged electrons. We know the cathode, in this case, is going to be the copper 2+. Then we know that because here is our copper chloride, copper 2 chloride for that matter. So we know that we're going to have copper 2+, plus, or I should put aqueous, plus 2 electrons. It's going to balance out to make copper solid. Okay. Last time we had copper working as our anode. This time it's working as a cathode. And that's just the way that the transfer of electrons is happening in this case. So if we multiply to make those number of electrons lost and gained, because we notice here we're trying to balance these electrons. Here we've got 3 electrons. Here we've got 2 electrons. We need those to match. So to match those, we need to do some multiplication. Multiply this whole side times 2. Multiply this whole side times 3. Just the 3 came from there. The 2 came from there. And that's how we can figure out how much we have to multiply it by. Sometimes you can find the least common multiple of those 2. Or least common denominator of them to get the right number, but you can always just multiply by the other ones. You might end up having some multiple of the real reaction. So if you have some common multiple in your final thing, you can always cut it down. But adding these together, multiplying them together first, we would get 2 chromium solid producing 2 chromium 3+ aqueous plus 6 electrons. The cathode reaction can be 3 copper 2+ aqueous plus 6 electrons produces 3 copper solids. So now we can combine these two equations into one final equation that we have. Notice we cancel out the electrons because we have the same number as reactants and products, so they end up being basically a spectator. And this leaves us with 2 chromium solid plus 3 copper 2+ aqueous is going to produce 2 chromium 3+ aqueous plus 3 copper solid. And that's it. So, I mean, right there we balanced our chemical equations and everything else like that. And we can also write out as a galvanic reaction, kind of in that cell notation. So in that cell notation, move back up a little bit so we can see right in blue. We started out with that chromium solid on this side. It went through this kind of buffer of that chromium trichloride or chromium 3 chloride. So I can say CrCl3. And if we know the molarity of that, we can actually put that molarity in. It's telling us that molarity So I can write it as 1 molar CrCl3. There's my, what I call the salt bridge, kind of the interface between one side from the other. The molarity of the other one is also 1 molar. This is copper CuCl2, and that's interfacing then with copper solid. My S turned into a 2. There you go. And that's kind of the cell notation for this reaction. So let's try another one. Here they're going to give us that chemical reaction, but we need to figure out the right cell notation for everything. Notice in this case that we have SN2 plus and zinc 2 plus, SN4 plus and zinc solid. So the zinc goes from a solid to an aqueous ion. So it's going to be acting as what we call an active, what do I call it? Active, can't remember the name for it now, electrode. An active electrode. The zinc, so it's going from a solid to an ionic, so it's losing these ions into the solution from the solid object. In this case, the SN4 is turning into SN2, so it's not actually ever a solid object, so it's not going to be one of our electrodes. So we're going to have to use some type of inert electrode for this, right? Need inert electrode. So for that, lose platinum. That's what they used previously. It's a good one. It doesn't really like to give off a lot of electrons in that regard. And we can then write out what's going on with these reactions. Looking at the one, it's always the anode as the start. And so the anode is the oxidation. The oxidation is the one that's losing electrons, which is going to be our zinc, because our zinc is going from a neutral charge to a positive charge, becoming more positive. So it's going to be losing those electrons. So on the left side, and I'll just write out the half reactions for them first. For the zinc, it goes from a solid, and it produces zinc 2 plus aqueous, plus must produce 2 electrons, balancing that charge on both sides of those reactions, right? And that's got to be our oxidation, which is the anode. The second one starts out SN4 plus aqueous, and that's producing SN2 plus aqueous. And the electrons are going to have to be a reactant just to balance the charge on both sides. So we have a 2 plus charge on the right side. We need to have a net charge of 2 plus on the left side to make sure that's balanced. And since the electrons are part of the reactants, we're gaining electrons on this compound, or this atom is gaining electrons. So we call that a reduction, which is the cathode. And for that cathode, since we don't actually have a solid cathode in there, the cathode is really our palladium, or our platinum. I keep saying the wrong word. Platinum is PT. So we can write this out now as our galvanic notation, our cell notation, saying that we start out with the anode, zinc solid, interfaces with, and they don't really tell us what it's interfacing with. So it produces some zinc 2 plus in aqueous solution. And there's some salt bridge in between there. There has to be to counterbalance that, but it doesn't really matter what we use as long as it has the right proportions to counterbalance that 2 plus charge. It's going to interface with the SN4 plus, comma SN2 plus. Here we have 2 different stages of that. Both of them are going to be aqueous, so I'm going to squeeze in an aqueous. and that interfaces through the platinum solid. And that's it. That's our basic notation for the cell. Just writing that out says that we have this galvanic cell. It tells us the type of electrodes we have in there, zinc and platinum. It tells us the mixture of solution that we have in there is going to be some zinc ions and some Sn +4 and +2 ions in there. And we just need to add that salt bridge to add the right counterbalance for things and figure out the right solutions to make for it. But a lot of those are just your spectator ions. They're not the actual reaction that's going on, so we don't mention them here in the notation. That's all I have for you today. I hope this helped you understand the idea of redox reactions and galvanic cells. Definitely, if you have any other questions, feel free to schedule a tutoring session with one of our great tutors through the Pinchi app. I always have tutoring hours on Monday afternoons from 3 to 5 and Fridays from 1 to 5. So right following this live stream, I have about 4 hours of tutoring hours. I would love to talk to you about chemistry or anything else that I can help with. Have a great week and enjoy yourselves. Portland State University. Today we are going to be talking about cell potential and the different types of potentials that are spontaneous or not spontaneous, different ways to calculate our Gibbs free energy or the change in Gibbs free energy. That's our delta G, and basically go from there. First off, I want to post a few links in our chat. Do this every week just so we have resources. There's a link to the Learning Center's website. That's pdx.edu/learning-center/tutoring. There's also a link to our Facebook and our Instagram. Follow us on Facebook and Instagram so you can get updates whenever we have new resources available for students. And let's get started. So today, I'm going to start off. Last week, we talked a lot about the galvanic cell, the spontaneous reaction that happens between two different chemicals in a chemical reaction. So we have those two jars. If you remember, we had a salt bridge kind of connecting them. Do a quick little drawing. So we had the two little things. We had the salt bridge that kind of connected through, and there was a electrode in each of them. And then we connected them with a wire, and we could tell the current going through this, which is a measure of the electrons passing from one to the other. And that would happen in a spontaneous reaction. You put it down and the current would spontaneously flow. The electrons are spontaneously moving from one to the other, and you'd end up basically causing a redox reaction, oxidation and a reduction reaction within those two different jars of solution. Today, we're going to talk about when this happens spontaneously, when it doesn't happen spontaneously. And we can figure out how to calculate the different values of how spontaneous it can be and relate that to the Gibbs free energy that we talked about in thermodynamics a few weeks back. So getting started, let's say this is cell potential. And we did that last week. We were talking about silver ions spontaneously reacting with copper. And it produced this flow of electrons between there. So we had a silver electrode and a copper electrode going into these jars. The jars had a solution of kind of a silver 2+ or copper plus salt solution going on in each of those jars. And there would be a reaction happening where the electrons would flow from the copper side to the silver side, producing more of the silver to solidify on the electrode and more of the copper to deteriorate away. I'm having trouble talking today. Deteriorate away. And this happens because there's a spontaneous flow of electrons going through there. Not all metals and not all two metals are going to spontaneously react. If we were to swap out that silver with lead, for example, or iron, they're not going to react in the same way that copper does. And we're going to see that now. So the spontaneous reaction, we can say, can be measured based on this potential of it to react. How much potential there is between the two cells. And that potential we can measure in voltage. And voltage is a common term we use for potential between two different objects. And it's always relative to those two things. So if you just have one solution there, there's really no potential because you're not relating it to another object. So it's always relatable. And we can use these potentials to basically define the cell potential. E of the cell would be equal to this E of the cathode minus E of the anode. And both of these values are standard values we can kind of look up on tables where they've already done a lot of this analysis for you and found the voltage potentials of those cells. And we relate them all back to this standard cell that we have, which is the standard hydrogen electrode, otherwise known as SHE. And that standard hydrogen electrode is really just, I'll write the equation for it, 2 hydrogen ions in aqueous solution plus 2 electrodes, or electrons, are going to produce hydrogen gas. And we're calling this kind of our baseline, kind of the center limit of all of it. So anything that happens on one side of that and related to this cell is we're going to call positive, and everything that happens the other way is going to be negative. All right, so in this case, the E of this cell is going to equal to 0 volts. And we can look up in a textbook or online these standard tables of cells. I can show you here. This is just the Appendix L in the OpenStax Chemistry 2 ebook, and they have basically these half reactions listed out and the potential voltages for each of them going down. And I've highlighted a few of them we're going to use today, so I don't have to search for them on the fly. Because some of them have negative values, some of them have positive values, some of them are larger or smaller, but they're all related to this standard hydrogen electrode as a base point. And we can use this relationship to that standard hydrogen electrode to see how they relate to each other using this equation that I wrote out. That's this equation here. Okay, by finding the that E of the cathode and then subtracting from that the E of the anode, whatever those values are on the table, we can find what the electric potential of that cell is. And depending on what those signs are, you can say if E, the electric potential of the cell, if that's going to be greater than 0 or a positive sign, we can say that's spontaneous. It's going to happen. The electron is going to freely move from one side to the other. If this is actually negative, or that potential is less than 0, this is not spontaneous. And in fact, it's actually going to work in the reverse order. So it'll be more of a reactant-favored reaction where everything's going to be moving to the left as opposed to moving to the right. So we can flip the whole reaction around, and we can see that in this case, these two have a relationship where if I know, let's say E cell is, a positive some value, some positive voltage, if I flip that reaction around, just making the products the reactants the products, then the non-spontaneous cell would be the same voltage, just as a negative value. And we'll go through some examples of that as well. So let's revisit now this galvanic cell that we looked at last week. Here's kind of an image of it here. See, they have the copper anode on the left, the silver cathode on the right. And you see the flow of electrons are going across the top and then back down in. The salt bridge is really just a spectator. It doesn't really have an effect on those voltage potentials. So what we want to do is we want to find out what's the electric potential of this. So if I write out the cell reaction that's happening, that's copper solid plus 2 Ag plus aqueous is going to produce copper 2 plus aqueous plus 2 silver solid. And notice the copper is losing electrons, becoming more positively charged. So it's going to be a oxidation reaction because oxidations lose electrons. The silver is gaining electrons, so it's going to be a reduction reaction. And we're going to write the different half reactions as follows, where the anode, remember the anode is always the one that's losing electrons. So that's going to be copper solid is going to produce copper 2 plus 2 electrons. And remember, you have to have that balance of charge on either side. So the 2 plus and the 2 minus there gives us a neutral copper solid. Writing out the cathode, that's just going to be our 2 silver plus aqueous. It's going to, I should add to that 2 electrons. Produces 2 of the silver solid. Those are just our half reactions that we were dealing with last week and when we talked about oxidation and reduction reactions. So now we can find the standard cell potentials of these 2 half reactions. So we're going to look for copper solid going to copper 2 plus. Switching over to my table. See, I had them highlighted. This one here, that's the 1 plus. I want to go to the 2 plus, the next line over. That's going to be this one, 0.34, and it's a positive value. So I can say then that the potential of this reaction, or half reaction, is equal to 0.34 volts. Looking at the silver, silver's that top one, 0.7996. 0.7996 volts. And to see this reaction, what the potential of the cell is, remember it's the potential of the cathode, right? So always the cathode first minus the potential of the anode. Equating that down, that's just 0.7996 volts minus 0.34 volts. We can already see, looking at the relationship between these two, this is going to be a positive value. And that's important. Oops. Clear. So that's 0.7996 minus 0.34, 4596. So that's equal to 0.4596 volts. That's a positive value. So that positive value says it's going to spontaneously happen. This reaction is spontaneous. And we saw that last week when we talked about the galvanic cell and how this was spontaneously happening when we just put those electrodes into the solution. Now we can compare that to lead, for example, swapping out the silver for lead and see how lead reacts with copper. And we can determine whether or not it's going to be a spontaneous reaction or not a spontaneous reaction before. Oops, I was still on my table. How's that? There's my iPad. Just to recap, I just plugged in the values we had from our table and did the math on there, and that was the 0.4596 volts. So we can swap out the silver in this case with lead and see what's the difference in reaction? Is there going to be a spontaneous reaction there, or is it not going to be a spontaneous reaction? So I'm going to do that here. Again, I'm going to start out by writing the full equation, chemical reaction that's happening. It's always good for reference. This is going to be lead 2 plus in aqueous solution produces copper 2 plus aqueous plus lead solid. So the question is, will this happen? And we can write out our half reactions. Again, our anode is still going to be the oxidation reaction. So it's the one that's losing its electrons. So that's still the copper. So this part of the reaction really hasn't changed. And it's going to have that same electric potential. Nothing changes because this electric potential value is related to that the SHE, the standard hydrogen electrode, okay, which is at 0 volts. So our copper half reaction is going to have that same potential of 0.34 volts. But in this case, we need to relook up what that cathode is. So in this case, I'll write out the cathode reaction. That's just going to be Pb2 plus aqueous plus 2 electrons. It's going to produce Pb solid. Big eraser, small eraser. Rewrite my solid a little bit cleaner. So we can see, we must see at least what that half reaction is going to be. Switching back to my browser, scroll down until I find lead. Here's lead here. We can see it's going to be negative 0.1262. So the cell potential, negative 1262. And there's a decimal place in there. That should have been a 0. 0.1262. Now we can find out the potential of the whole cell simply by taking that negative value, negative 1.62. We're going to minus from that the anode. Again, this is in volts, minus 0.34 volts. We could already see, just looking at these values, a negative minus a positive is going to give us a negative value, which means it's not going to be a spontaneous reaction. We can do the math on that. Just tell us basically how non-spontaneous it's going to be. And you can see 0.4662. It's a negative 0.4662. So that's the voltage potential of copper and lead together. And see, since it's a negative value, this is not spontaneous. And it actually has the opposite potential almost of the silver and copper. So in fact, if we were to put this in a galvanic cell together and have that cell potential being negative, this will actually work in the opposite direction. So this reaction would go to the reactant side, producing more copper 2 plus from any, more lead 2 plus from any copper 2 plus that we had. Because you can reverse this around, just flipping that reaction, writing it Cu 2 plus aqueous plus lead solid will produce copper solid plus lead 2 plus aqueous. And this cell potential will equal the negative of the cell potential up here. And since it's already negative, that makes a positive 0.4662. So we won't get more lead solid. We'll end up getting more copper solid in that reaction. So we can flip those cells around. It'll actually work in the backwards direction. So let's try another reaction. That was the one that kind of we were looking at last week. This next one we're going to look at is, it says to use data in the table. I like to use the appendix. Should be the same value. To predict the spontaneity of the oxidation of bromide ion by the molecular iodide under standard state conditions. And support that prediction by calculating the standard cell potential for the reaction. So calculate the standard cell potential for the reaction. And then repeat it basically for the reverse reaction. So just writing out what this reaction is. This is the oxidation of bromide by molecular iodide. So molecular iodide is this guy here, I2, in a solid form. Would that be a solid form? Let me double check to make sure. I thought I2 was a liquid. I think it's a liquid. I guess book says it's a solid. We'll stick with it. So we're going to add to that 2 Br minus in aqueous solution. So bromine ions. That's going to produce 2 iodine ions, iodide, aqueous, plus Br2, liquid. So that's our reaction, our half reactions that we're going to have in there. The anode for it is going to be that oxidation reaction. And since the oxidation is the one that loses electrons, in this case the bromine is the one actually losing electrons. So I can say that the anode is equal to 2 Br minus aqueous which produces Br2 plus 2 electrons. The cathode, the reduction half reaction, is gaining those electrons. So this is going to be I2 solid plus 2 electrons. It's going to produce 2 iodine minus aqueous. Again, we have that balance of charge on either side of it. That balance of charge is very important. Make sure that you have the electrons on the right side of that reaction. So going back to our table, we need to look up what these standard potentials are for both of these guys. Switching back, I want to look for bromine first. There it is. 1.0873. Scrolling down to iodide. There we are. That's 0.5355. And they're both positive. Yep. So I just wrote those there. Now we can find the potential of this cell, which is going to equal always the cathode first, 0.5355 volts, minus the potential of the anode, which is 1.0873 volts. I'm going to do the math. 0.5 355 minus 1.0873 is a negative 5518. So negative 0.5518 volts. So the question is this going to be a spontaneous reaction? The answer is not spontaneous, because we have a negative voltage and the negative voltage potential of the cell. But what about the reverse reaction for the oxidation of iodine ion by molecular bromine? Well, if we flip that around, that's just flipping around this reaction up top here. If I do that, I will get 2I minus aqueous plus Br2 liquid producing I2 solid plus 2Br minus aqueous. And since we know the two cell potentials are the same, those two are going to be the same. And we're just looking at, you're really just swapping the anode and the cathode. So doing the math of the cell, this is just going to be equal to 1.0873 volts minus 0.5355 volts. And that's going to be just the negative of this value here. There it is, or the positive of that value, I guess. So that would be spontaneous reaction. So you can see by swapping the order of these, we can really see the direction it goes. We don't really have to do all the math for it, because once we found this, we know that if you put those two in a galvanic cell, the potential between them is going to cause the reaction to move towards, in this case, the reactant side, or towards the product side when I write it like that. Because by swapping it around, all we're really doing is changing the sign of the cell potential. Excuse me. Now, since we are talking about this cell potential relating us to the spontaneity of a reaction occurring, if we remember when we talked about thermodynamics, the spontaneity of something happening was really determined by the change in Gibbs free energy. That standard change in Gibbs free energy, if it was a negative value, was a spontaneous reaction. If it was a positive value, it wasn't a spontaneous reaction. And Gibbs free energy took into account the enthalpy and entropy of the system to find that Gibbs free energy. So the cell potential is kind of an easier way, if you've got voltage meter around and stuff like that, to determine what those voltages are. You can also just look them up on tables as well. So there's a relationship between the cell potential and the change in Gibbs free energy. This is between potential and, we'll just say, thermodynamic properties. Which we had delta G, and we also defined a K. And we had a relationship for delta G, an equation between there, where delta G was equal to, we said the negative of the gas constant times the temperature by the natural log of K. That was what we were talking about before when we had that delta G to K relationship. We could also calculate it based off of the enthalpy and entropy, but in this case we're talking about specifically the thermodynamic property K. And delta G can also be related to, because it's the standard free energy of change, this value of the potential of the cell, which is proportional to delta G. As we saw, they both, the potential of the cell is positive when the delta G is going to be negative. And there's some proportionality constants in there. We can write that, which is equal to negative N, N being the number of moles in the reaction, times F. F is a Faraday constant, times the E, the potential of that cell. So N equals the number of moles. F is equal to Faraday constant. And that Faraday constant is really related to two other constants, which is the charge of an electron being 1.6 times 10 to the negative 19 coulomb times Avogadro's number, which is the number of something per mole, right? Which is, I need to move that over a little bit, 6.022 times 10 to the 23rd. In this case, it would be electrons per mole. So I'll just write it as a per mole. So if you multiply those two together, you get the Faraday constant, which is 96485.3 coulombs per mole. It's just a constant value. Faraday was not, he lived before they found out the charge of the electron, so he just found that proportionality constant. And later on, other physicists broke it down and figured out what the charge of the electron was and the relationship between Avogadro's number. But we can use these values now to relate the electric cell potential to the Gibbs free energy, or the change in the Gibbs free energy. So if I equate those two to each other, I can see that negative RT ln of K is equal to N, or negative NF E of the cell. And I can solve both of those. That's just rearranging the equation around a little bit to solve for either K or for the E of the cell, the cell potential. So let's solve for cell potential. That's going to equal basically what's on the left-hand side, RT ln K. But we're going to divide it by these values here, the coefficients of that cell potential on the left, or on the right side now. So divided by negative NF. We see that some things cancel out, mainly the negative signs. We end up with RT over NF times the natural log of K. So I didn't mention it, but R is your gas constant, right? Which is 8 point, what did I have it as? 8.1, 8.031466. That's in joules per mole Kelvin. And the temperature is always going to be that temperature in Kelvin. So if they give you in Celsius, you can convert it by just adding to it 273.15 or just 273. If it's in Fahrenheit, you have to do a little bit more conversion, but it's not too bad. We have here now this relationship between the E of the cell and this value, RT over NF, natural log of K. Since we usually talk about our K values in scientific notation, that's 10 to the power of something, we can convert that natural log to a log base 10 by using a change of base formula, which essentially results in this equaling, just multiplying it by a factor of 2.303 to get log K there instead. And that makes it a little easier, so instead of taking it e to the power of, we end up taking it log to the power of, or 10 to the power of, to find that K value. So writing that down a little bit, my cell potential, just rewriting RT over NF times 2.303 log of K. What I want to do is divide by all of this, because that solves for the log of K. When I do that, I'm just going to maneuver my math around here. My N and F, since they're on the, can move up to the top there, and I'm left with something along the lines of this, where the moles times the Faraday constant times the cell potential, all divided by the gas constant times the energy times that change of base formula. 2.303 is going to equal the log of K, log base 10. And now I can take everything 10 to the power of on either side of the equation. So 10 to the power of that fraction is going to give me the value for K, because 10 to the power of log of K is just equal to K. Put the little caret there so you can see that it's this whole fraction that's part of the exponent. So that's a really good equation to have handy. There's a few of them here I'm going to highlight. That one there. This one here is a new one. You should already have this one either memorized or on a note sheet up on top there, because these are values you can find in your delta G or K, the relationship between them. Here we have the relationship between delta G and the energy of the cell. And then down here we have the relationship between the potential of that cell and that K value. So between, this one's really derived from these two up top. But between those three equations, if you have any two of those values, you can always find the third. And the textbook had this nice triangle. I love this triangle. I shared with you like the pH square before, where if you could find your pH as you go back and forth between pH and concentration and pKa and other things. This is similar, but it's more of a triangle. It's that relationship between your Gibbs free energy, the electric potential of a cell, and your K value, and the equations you would use to convert back and forth between them. So here, if you have the K value, you can just plug it in. You also need to know the temperature, but usually that's at standard values. And then the Faraday and the gas constant are both constants, and N is just the number of moles. So that'll solve you for K. If you had this and you want to solve for K, just rearrange that equation to solve for that K. Similar going to delta G from E, that's just this one we talked about today. Again, the Faraday is just a constant, N is just the number of moles, and E is that potential, the cell potential. So if you know that, you can find Gibbs free energy, or you can rearrange and solve for the cell potential if you know Gibbs free energy. And we talked about this a few weeks ago, so it's the same idea. Converting from K to delta G is really useful to be able to do. There's also this nice table when they talk about the relative nature of these. If K is greater than 1, and if delta G is less than 0, or if the cell potential is greater than 0, the reaction is spontaneous under standard conditions. The products are going to be more abundant at equilibrium. If K is less than 1 and delta G is delta G is greater than 0 and the cell potential is less than 0. So cell potential is negative, delta G, Gibbs free energy is going to be positive. This is not a spontaneous reaction. The reactants are abundant at equilibrium. If everything's equal, the reaction is at equilibrium under standard conditions. So that means once they're at equilibrium, the change back and forth is basically equal to each other. The concentration is going to stay relatively the same. So let's use this now to try to solve for these values given a reaction. So what is the standard free energy change of the equilibrium constant for the following reaction at room temperature? Room temperature, we're going to say, is 25 degrees C, or 298.15 Kelvin. You can see the reaction here. SN2 solid plus 2Cu2 plus aqueous is in equilibrium with SN2 plus aqueous plus 2Cu plus. Excuse me. Notice we're not producing a solid here. We're just producing the solid there, which means we're going to have some type of spectator. Not really a spectator. It's an inactive electrode versus the active electrode. So something like palladium or something in there instead of copper. Copper is going to be existing in an aqueous form only. It won't be one of our electrodes in our cell. That's okay. It doesn't really matter when we're coming through the anode and cathode reactions. If we were going to write this as cell notation, we would have to take that platinum or something in some other electrode into account. So to remind us of what that equation is, I'll write it here. This is the cell potential of the cathode minus the cell potential of the anode. And we can write this out. The anode is the oxidation. And that oxidation reaction is always going to be the one that's losing the electrons. In this case, that's the SN solid, because it is producing SN2 plus, this is aqueous, plus 2 electrons. It's losing those electrons. It's becoming more positively charged. The cathode, this is our reduction. This is basically 2. Notice there's a 2 in front of these guys. So I'm going to say 2 times this whole reaction. Cu2 plus aqueous plus 1 electron produces Cu plus aqueous. So that's that half reaction there. But really it's that Cu2 plus to Cu plus reaction that we want to look at and find out what is the voltage potential of that. Give me a little bit extra space. And I need to look up now on my table what are, not the cell, what are my voltage potentials of these half reactions? So let's start with that copper reaction, because we're moving alphabetically. Here's my table here in Appendix L, going down B, C. I had it, I lost it. Oh, that's C, that's why. Cu is down here. That's this one, that's 0.135, or 153. Notice that that reaction from 2 plus to solid has a greater voltage potential. The reaction from 2 plus to plus has a much smaller voltage potential. So I'll write that here on my tablet that you can't see yet. We're going to find the SN. It's down here, negative 0.1375. Negative 0.1375 volts. So you can see I wrote the cell potentials here on the left. And I can use this equation, that potential of the cathode minus the potential of the anode, to find that potential of the cell. So that's going to be 0.153 volts, the cathode potential, minus a negative 0.1375. That minus the negative is really going to make this a positive. We distribute that negative in, gives us a positive value. This is going to be a positive value, so right there I know it's a spontaneous value. So this reaction is going to happen without too much extra help from us. We can do the math on it. Where'd my calculator go? There it is. 0.153. I'll just use plus. If you didn't, you could use that minus. And then I like to put parentheses around it before I put that negative. 0.1375. And it gives us a positive 0.2905. And that's the number of volts in our cell potential. So we already know it's a spontaneous reaction. Let's check for a delta G value. What does delta G tell us? Using this same voltage that we just calculated, we can say that negative N times Fe of the cell potential. So plugging that in, remember N is equal to 2 in this case because of that 2 there. We need to be making 2 moles of this. And then F was equal to 96,485.3. And the units were coulombs per mole. And we have our voltage there. Excuse me. And the voltage is up on top here. So multiplying that out, negative 2, I'll just write times F for now, times our 0.2905 volts. And that coulombs times volts is going to give us joules. So we end up with joules per mole in there, which is the units for our change in Gibbs free energy. You can do it to kilojoules depending on the units that you end up with. So plugging that in, 2 times, I'm going to write 9648.5.3. That's the Faraday constant times our cell potential. And this should really be times negative 1 because I forgot to put the negative sign in there. So that's 56,057.96. So I'm going to say 56.097 kilojoules per mole. So I just bumped it up to kilojoules because we had a value in the thousands of joules. So that's our delta G. Notice it's a, oops, it should be a negative. Notice it's a negative. That's what I want to say. It's a negative value, which corresponds with a positive value up here, saying that this is a spontaneous reaction. It's going to happen. Last part is calculating our K value. So that, we can use this energy potential of the cell is equal to RT over NF ln of K. And remember, we can convert that to NF 2.303 log of K. Because all we did here, this extra factor in here converts this natural log of K to the log of K. Sometimes log base 10 is a lot easier to use than natural log. So plugging in our values for this, we can rearrange it in this form. I like to do that a little bit easier. So that's of the potential of the cell times, I'm just going to multiply by the two denominators down here. So that's times the moles times the Faraday constant. And then we're going to divide it all by the numerators up on the top. So that's the gas constant, the temperature, and we're going to multiply that by 2.303, and that's going to equal the log of K. So we have values for all of these. We know N is equal to 2. We know the Faraday constant is equal to 96,485.3. We know our gas constant is 8.3146 joules per mole per Kelvin. And the temperature we said was 298.15 Kelvin. So we should be able to solve. We got all the values we need in here. We just got to plug them into everything. So I'm going to write it all out in a big long thing. 0.2905 volts times 2 times our Faraday constant, which is 96,485.3. We're going to divide that by our gas constant, 8.31466. We're going to multiply that on the bottom by our temperature, 298.15. A lot of books let you get away with 298, which is probably fine. I like to add that extra couple decimal places in there. And then we're just that 2.303. That's going to equal log of K. So let's plug that in our calculator. 0.2905 times 2 times 96485.3. So I'm going to divide this whole thing, and I'm going to put a parenthesis there because I want to make sure I'm dividing by all three of those values. 8.31466 times 298.15 times 3.303. And that gives us 981 point, let's just say 982. That's equal to 982. So I want to take this 9.82. So I can take this value now and take it all to the power of 10. What? End up with a really large value. Am I doing that right? Faraday constant, E cell, 10 to the power of is equal to K. Yeah, I'm doing that right. Okay. What I needed to do is make sure I was in scientific notation. That's better. So when I take each of these to the power of 10, 10 to the power of log of K is going to equal K. So this side of the equation gives me K. 10 to the power of 9.82 gives me this 6.6 times 10 to the 9, which is our value of K. And that's it. So that's how we can solve for the different thermodynamic properties of the reactions that are happening within our cell. We can solve for that delta G, the potential of the cell, and that K value just by looking up a few simple voltage parameters on the tables. Again, that's going to be Appendix L in your textbook, chemistry, the OpenStax Chemistry 2E textbook gives you all of those tabulated voltage parameters. And those voltage potentials are all going to be related to that standard hydrogen cell or standard hydrogen electrode, which is at 0 volts. So everything relates to that. And we're using that relationship to find the potential difference between the anodes and cathodes of our reactions. I'll see you again next week. I hope you have a great week and enjoy yourself. As always, feel free to stop by the tutoring center or really stop into Penji and create an appointment with one of our great chemistry tutors, or we also have tutors in various other subjects: math, physics, science, biology, languages, and academic coaching for people to help you kind of find your way in school. Have a great week and enjoy.